Okay, so we're gonna go over quiz number 6. Let me go ahead and share the screen. Okay, quiz number 6. Okay, so this is a quiz number 6. So you know, just kind of follow through with your what you have on your answer sheet, and then just kind of take notes. Okay, so you can be able to later on. You need to go back and redo some of these if you have some problem with it, and so that way get you ready to do for the final exam. You will see some of these questions again, so make sure you be prepared. Okay, so the first one for the question number 1, they want to find the net reactant of X. So that doesn't deal with just the X. X value is this one right here, XC or XL, okay? So you look at both of these, so you look at the comparison between the two. And so the difference is about 50 ohms. So XL minus XC. So X, yeah, let me go ahead and enlarge this one a little bit. So so X equals XL minus XC. So therefore 80 ohms minus 30 ohms equals 30 ohms. Okay. And so this one is going to be inductive because the XL is much greater than XC. So this is represent inductive circuit. So so number 2, the answer is inductive. And number 3, the total impedance. Okay, so total impedance, you have to use the calculation ZT. Okay, so ZT equals the square root of the quantity R squared plus X squared. Okay, so we know that R squared is R is 50 ohms, so 50 ohms square plus 50 ohms square. So you take you square that and then you add it together. Take the square root of it. That gives you 70.7 ohms. So ZT equal to 70.7 ohms. Okay, right here. All right, so next thing you want to do after that, once you have the impedance, now we can use it to calculate the total current. So total current, or IT, equal VT divided by ZT. Okay, so therefore IT, VT is 100 volt VAC right here. Okay, on the circuit, divided by 70.7 ohms, that yield 1.414 amps. Okay, so make sure you remember that. So IT is 1.41 amps. Okay, so therefore this is what your circuit looks like. So if you're converting all this information into a circuit to an XY axis, would be something like this. XL would be pointing up 80 ohms. XC is pointing down to the bottom 30 ohms, and then XR would be going to R going toward the R side, which is about 50 ohms. Okay, and so therefore this one is going up, this one's going down. So combine these two together and leave you the greater amount will be the XL by 50 ohms. Okay, so that's why we got an inductive circuit. So that's a question number 1, 2, 3, and 4. Okay, any question on that? Okay, no question. We'll move on to the next one. Okay, so now they want to know now they want to find the voltage across R1. So that's question number 5. So now if, VR1 equals I total times R, or equal to 1.414 amps times 50 ohms, which yields 70.7 VAC. And then so number 5 is 70.7 volt or 70.5 VAC. That's fine. And then number 6, voltage across C1. So VC equal to the quantity I total times VXC. Okay, so 1.414 milliamps times 30 ohms equals, so your answer is equal to 42.42 VAC or 42.3 VAC. That's fine. Okay. So, and then your XL, so XL equal to I total times XL, so 1.414 milliamps times 80, 1.414 amps times 80, that's yield 113.13 VAC. So VL is going to be, yeah, approximately about 112, 113, okay, so And then after that, they want to calculate the phase angle. Okay, so the phase, so this is going to be inductive circuit because the XL of the voltage in the L side is going to be much greater than the VC. So this is inductive circuit. Okay, inductive circuit, voltage lead current. So therefore, we're going to expect a positive angle. Okay, so phase angle is equals arctangent of the quantity Vx over Vr. Okay, arctangent equals, so phase angle is equal arctangent of 70.1 VAC divided by 70.1 VAC. That will be giving you a 45 degree. Okay. So this is what you have is just like I said, it's so you have the VL, VL is going up, so 113.1 volt, and then VC is going to go down 42.4 volt, and VR is going here 70.7 volt, and then we combine these. So this one is on the x-axis, so therefore we combine together, leave you more value is toward the inductive side, leave about 70.7 volt. Okay. So now we just move that 70.7 volt to the other side. So now we have this one here and we form that triangle and you get this phase angle. So that's how we do that calculation, why it's become positive angles, not negative. Okay. So any question on this question number 5 to 8?
Can you slide your screen back over to the left real quick, please?
Okay. Right here.
Thank you.
You're welcome. Okay.
I have a question.
Yes, go ahead.
The phase angle
Yes.
you calculate with the voltage can be calculated with the impedance.
Yeah, you can definitely, for a series circuit, yes, you can do a calculator with impedance. Okay. It's almost like right here. Okay, it will be the same thing. You move this one toward this side, you're moving this one over here.
Okay.
And then you put in, and then you put another here, and then you put an angle. So it's going to be arctangent of 50 over 50.
Okay.
Okay, and then you still will come up to exactly 45 degrees.
Thank you.
You're welcome. Okay, any other question? Okay, everybody's good. All right, next one. Okay, so the next one is going to be this one here. So, okay, so question number 9. Okay, they want the current resist. Okay, so we want a current resist. Okay, current through a resistor, IR. So therefore, IR equal VT divided by R. Okay, so we know that VT is 50 VAC divided by R is 5K. So therefore, we got 10 milliamps. Okay, so IR is 10 milliamps. So that's number 9. Number 10 is inductive current, IL. So therefore, IL equal VT divided by XL. Okay, so 50 VAC divided by 4 ohms, 4 kilo ohms here. That yields 12.5 milliamps. So IL is 12.5 milliamp. And then number 11, capacitive current IC. So IC equal VT divided by XC. So 50 VAC divided by 2.5 kilo ohm. So that's give you 20 milliamps. Okay. So 20 milliamps, that's IC is 20 milliamps. Okay. So this is when you're doing a parallel, the only thing that changes is the current. So therefore, we have to compare the two current together. So we compare the IC and IL. Look like IC is much greater than IL. So therefore, this circuit is going to be capacitive circuit. And we know that current is going to be leading the voltage in a capacitive circuit. Okay, so I did calculate the IX, so that's IC minus IL, and we're going to use this one in the next step. Okay, look like I did right here. So your IC is going pointing up 20 milliamps. IL is going to go down because it's lagging in currents. Okay, so that's 12.5, and then IR is going to be 10 milliamps. So, and then we can combine these two together because they're on the y-axis. So therefore, this one goes up and then it goes down by 12.5, leaving you about 7.5 milliamps left. Okay, so that's why we have this is 7.5, and then we're going to compare these two together to get the phase angle. Okay, so any question on question number 9 to 12? Okay, so next one. Okay, so the number 13, they want total current, IT. Okay, so IT equal to square root of the quantity IR squared plus IX squared. Okay, and we calculated a minute ago. So square root of the quantity 10 milliamp square plus 7.5 milliamp square. And then we take that and then we do the calculation. It comes to 12.5 milliamp. Okay, so that's IT is 12.5 milliamp. Okay, so ZT equal VT divided by IT, which equal to VT is 50 volt AC divided by 12.5 milliamps equals 4 kilo ohm. Okay, so that's 4 kilo ohm is the ZT or the total impedance for number 14. Okay, number 15, the phase angle between VT and IT. Okay, so phase angle is the same thing. We look at arctangent of the quantity IX over IR. So theta equal arctangent of negative equal the quantity 7.5 milliamps divided by 10 milliamps. And then we take that and do the calculation. Comes up to 36.86 degrees. Okay, where do we get that? We get it directly from here, just like we just talked a minute ago. Okay, so it's coming from this one right here. So like I said, when I do the combine whatever on the y axis on the xi axis here, leave you just a 7.5 milliamps over this one. So I slide this one to the other side, and then we can created this one, and you got your little angle right in this your phase angle right there, and it's in the positive, it's in the first quadrant, so it's positive angles. That's why we get a positive angle here. Okay, so that's what we have for there. So like I said, the answer for number 15, the phase angle is 36 degree. So anybody have any question number 13 to 15?
I see what happened on that. The book got a negative angle, but I think what happened is the book doesn't say it, but it's in a different quadrant.
Yeah, so like I said, because we have combined these together, right? Because we got so the x and the ix, we combine these together because they're in the same line here. So therefore, if something goes up to 20 and then it goes down by 12.5, so 12.5 goes down somewhere here and then it stops right here. So therefore, from here to this point would be approximately about 7.5 milliamps left. And then it's toward the IC direction. And then we know the IC, the currents lead voltage. So therefore we're going to have an angle that is going to be positive. That's why it's right here. So that's why when you combine together and move this one over, and that's why your angle is in the first quadrant here, and it's always going to be a positive angle. Okay, so positive here. So there's the second quadrant, third quadrant, and fourth quadrant here.
Yeah, I agree with you saying. I'm just that I got this book and they didn't explain that aspect of it.
Okay.
It was a difference in the quadrant.
Okay.
But
So
I agree with what you're saying.
okay, so you follow exactly the logic that I go through. Okay.
Exactly.
Okay, very good. Okay, so anybody have any question on 13 to 15? Okay, so like we said, like Mr. Pham always said, make sure you go through this again several times. So just go through it, even work into the same circuit. Make sure you know how to do this simple basic calculation, because you will see it again in your final. So just be prepared. All right. So that's pretty much it on my part. So if anybody have any question, anything about the homework, please bring it up and we'll try to answer it before Mr. Pham start the lecture.
Can I see number 8 again, please?
Yes, okay, number 8. Okay, number 8 would be here. Okay, so that's 8. Okay, so phase angle is going to be 45 degree. Okay.
VX divided VR.
Yes.
Okay.
So this is the formulas right here, phase angles, and then we got the, okay.
I do another way, but I got 45 too.
Okay, well, if you got 45 too, good for you. Okay, so good. But did you follow the logic that we go through to find out how this come about?
This
Okay.
new one.
Okay, it's just the same thing as this one right here. I'm just translating from here to the graph. Okay.
Okay.
So therefore, so I calculate VR, VR1, VC, VL, okay? So therefore now I have to do is just look at that and I just put it into the graph, okay? So here's my VL, it's, okay, so my VL is going to be pointing to the positive side because in an inductor, voltage lead current, so therefore when it's leading, it's pointing up. Anything lagging, it's pointing toward the bottom. And in capacitor, the voltage lag current. So therefore, that's why this one, the VC is pointing down by 40.4 volt. Okay. And so, and then you got VR would be here. So VR is 70.7 VAC. And then now we can combine the one that is on the VX axis. So therefore, we combine this one together, this one here. And so leaving you with just the 70.7 volt pointing up because the VL would be much greater. Okay, so and then after that, I sort of look at that, and so now I'm moving that the VX from that was on this line to the other side, so I can create this angle. Okay, see VX that was on this line. Now I just move it, slide it over here. Okay, so that's still 70, and then my adjacent side, and then my hypotenuse or your VT, your total input voltage, which is right here. Okay, and that's here. Okay, so and then we just follow the trigonometric function. They said tangent of the angle theta is equal to opposite over adjacent. So opposite would be Vx over VR. So that's why we got this formula right here, and that's where we got the formula, which is the formula right here. Okay, so and then we pop in that value in and do our calculation, and it should come out to 45 degrees. Okay.
X divide R. So okay, thank you.
You're welcome. Okay. So any other question?
I
No.
think we had the same thing. You gotta remember what quadrant.
Yeah, just quadrant. Yeah, you just have to do just think about, you look at the two, right? You look at whatever in the Vx, which is greater, which one is greater, and that would be the total would be, it would be more toward pointing the upward toward the VL. And that's why this one stays this one by 70.7. So therefore, this is more inductive circuit. And we know that inductive voltage lead current. So therefore, we're going to know that the angles is going to be positive because they say lead is almost positive. Anything that lagging, then your angle would be negative.
Okay.
Okay.
Thank you.
You're welcome. Okay. Hopefully that's clear for everyone. Okay. Thank you, Mr. Pham. Back to you.
Thank you, Sam, man.
You're welcome.
Okay, so today we will be learning about the filter. We only get the filter, then we get the resonance. I try to give it to you not the very, very important on the AC before we can get a minute. Okay, what I'm saying is we try to get through very important subject on the AC circuitry. That means we still get the passive filter and the resonance. Okay, then after that, I can go back with these few things. we're not done. Like I can teach you how to solving the RC, RL, or RCL circuitry, but we're using different way, complex number, okay? But that normally when you go to the college, then you have to learn. But in here, we're not emphasizing on that, okay? So now we're talking about filter. Basically, you get two different. One they call a passive filter. That means in the circuitry, they're using RCL. That means just a passive component. However, in electronics, you can learn the same thing. They're working exactly the same, but they call active filter. That means they're using the op-amp, operational amplifier, adding to RC to build the filter that will be active, okay? Right now, we're talking about passive in the AC circuitry. Okay, filter are circuit that capable to passing signal with a certain selected frequency while rejecting signal with other frequency. Okay, this property called selectivity. You understand the filter, they allow a certain signal to pass through it. Okay, and the other thing, they will be blocked. For example, your cell phone, you need the filter. Okay, so your TV, they get the filter. The thing is you understand on the TV, the signal coming in, they the same wire. However, they include your voice. They include the picture. Okay? That means they have to get the filter. Your voice, they allow to go to the speaker. The signal, they allow to display on the TV. So they must get the filter. Okay? Passive filter, URCRL or RCL circuitry. Passive circuit provide frequency selectivity. That means RCRL, RCL. The four basic categories of passive filter will be low pass filter, high pass filter, band pass filter, and band stop filter. Also the other name, notch filter. Okay, make sure if you get any question, just go ahead and stop me, okay? Now, first thing we're talking about low pass filter. This chapter very, very important for your technician job, okay? So you have to be careful. This is the output from the low pass filter. That's the ideal filter, okay? 0 dB, what that means in here? That display for the AV voltage gain and this stands for frequency. That means the frequency domain. Okay. So this is the ideal low pass filter. So 0 dB. How much you understand about 0 dB? 0 decibel.
In equal out.
0 dB. They're telling you what the gain equal. What is the gain equal? You see that the gain equal V out divided to V in. So if 0 dB, what the gain equal?
1.
1, correct. If you don't know, then you go ahead and take 20 log of 1. Okay, let's see. KB equal 1. You get AV equal 0 dB. Okay, and basically they will be equal V out divide V in. And now, if you take the log AV equal 20 times log of V out divide V in. Okay, and they equal 0. Okay, that means you get V out equal V in. V out equal V in, only telling you no log. Okay, there will be a no log in here. You apply 10 volt, they coming out 10 volt. That means you not lost anything. What the name of the part right here? Who knows? If you don't know, I'm telling you, try to remember.
Remember.
Mid-range. Okay? That will telling you that range gain equal what? Okay? That's what we call a mid-range. And for the ideal filter, they go down to the cutoff FC, mean cutoff frequency. Okay, cutoff frequency. What is the cutoff frequency? You can get a different name. Okay? Critical frequency. What else? Cutoff critical frequency. Oh no, what else? That's what you must be memorized. Okay? You interview for the job. You have to answer. Okay, you get cutoff
Corner,
frequency. Also,
critical,
yeah. The next one, critical. Frequency. I want to make sure next one. You guys have to tell me.
corner,
Corner. Frequency. I want one more.
Break, break, break. Break, B-R-E-A-K.
Yeah, break frequency. Either one, they're still the same cutoff frequency. Okay? Otherwise, they're talking about corner frequency. You don't know what is corner frequency. Now, what is the cutoff frequency? What is it?
Where it goes down to minus 3 dB.
Exactly. Okay? That means at that frequency, output down 3 dB. Okay? Ah, 70.7%. Seventy point 7%. Okay, equivalent 0.707. You know why? How come you get minus 3 dB? Okay, that means they take 20 times log 0.707. You get minus 3 dB. Okay, so the important to you. Whenever they're talking about cutoff frequency, that means at that frequency, output will be going down, minus 3 dB. That is the way to talking, but not the way to calculation. If you want to doing a calculation, you have to using 0.707. For example, you get 10 volts coming out, okay? At the cutoff frequency, they going down 3 dB. In order to find out what is the output, then you have to take 10 times 0.707. Then you get 7.07 volt. You can see the difference when they're talking about minus 3 dB, but you cannot using minus 3 dB to do your calculation. Remember, they have to be using 0.707. However, by the way, for the power at the cutoff, the same thing will be going down. How much they going down?
One half. One half.
Perfect. 0.5, one half for the power. However, for the voltage will be 70.7%. Okay, is that make it clear for you guys? Now,
Put down 1/2 for the power.
right. We already did doing that. Okay. Now, going back here, we go to basically practical filter. Okay. So on the practical filter, at the cutoff, okay, they going down minus 3 dB. Remember again, equivalent 0.707. Okay, if you get the output input 10 volt, so in the mid-range here, okay, output also is 10. You not lost anything. However, at the cutoff frequency, this point right here, you will be going down 3 dB. That means 0.707. So at this point, output only 7.07 volt. Okay, and now they keep going down. What they said, slope minus 20 dB per decade. You understand a decade is 10. For example, cut off 1 kilohertz. Okay, so they will be going down 20 dB per decade. That means 10 times of the cutoff. If you get your cutoff 1K, 10 times you get 10K. Okay, then they keep going down with the slope minus 20 dB. How come you get the number minus 20 dB? The thing that I want to tell you, you cannot do anything with minus 20 dB. You have to know the number. Okay, then I can tell you minus 20 dB. Okay, they will be the same equal 20 times
20 log,
log of what number?
V out over VN.
Yeah, V out over V in. But I want to see what the number equivalent to minus 20 dB. Like, you say, okay,
Well, Mr. Pham, you could put an X or whatever number letter you want there and then solve for it.
now what I said, you must be memorized. For example, we're talking about minus 3 dB. You must be understand that will be 0.7.
Oh, you mean like 0.1 or 0.1 or something like that.
That's what I want you to know. Okay? 0.1.
1.
Okay? That will be equal minus 20 dB. Okay, so for the input 10 volt, okay, input equal 10 volt, okay, then, okay, they down 20 dB, minus 20 dB. Output should be how many?
You want like 0.001 or something?
That means you have to get your 10 volt time what? 0.1.
0, 0.01? Okay.
The thing is 0.1 equivalent to minus 20 dB. They're telling you the output now they will be equal 1 volt. That's how do we do the calculation. By the way, I can be telling you, okay, minus 40 dB equal 20 log of what number?
0.1, and then you say minus 40 dB is
0.1,
0.1.
0.01. That same thing, minus 40 dB. Okay, so at a minus 40 dB, what output? In this example, what output? You take 10 volt time
0.01.
0.01, and that will be telling you 0.1, right? That will be helping you how to do your calculation. Okay, so if you're looking into here for the low pass filter, they allow any signal with a zero frequency, that means a DC, up to the cutoff frequency. They allow those signals to pass. So that's why they call pass band. And also this is the bandwidth of this filter. After the cutoff, they don't care. The thing is they want to cut it off quickly, as much as possible. Okay? Only signal from 0 here up to the FC, they allow to get through the filter. That's what we call a bandwidth or band path. After the cutoff, they supposed to be stop band. They don't want to stop it. That's a basic for the low pass filter. Either passive or active filter. They work identical. So any question? How the low pass filter working? Okay, if not, we go next. Now, one pole low pass filter. That means when you get a circuitry, only one resistor and only one capacitor. That's what they call one pole. Low pass filter only allow low frequency signal from 0 Hz to its cut-off frequency to pass while blocking those any frequency higher. To do the calculation for the cutoff frequency, they're using the formula FC equal 1 over 2 pi RC. In this formula, F will be in Hz, R will be in Ohm, and C must be in Farad. Okay? At cutoff frequency, the gain, that means V out divided to V in, down minus 3 dB, or the output going down to 70.7%, same as 0.707 of its maximum value. After the cutoff, output decrease at a constant rate, okay, at the frequency when the frequency increase. That is when the frequency increase tenfold, 1 decade. The voltage gain is divided by 10. In other words, the gain decrease, okay, 20 dB. Each time the frequency increase by 10. That's what we already talked to you. Okay? On this part in here, you need to memorize. First thing, one pole LPF. How do we know that is one pole? That means the circuitry gets one resistor and one capacitor. And you can see later on, 2 pole. That means you get 2 resistor, 2 capacitor. And 3 pole, same thing. 3 resistor, 3 capacitor, and so on. Okay? And the next thing, you must be memorize how to doing calculation for the cutoff frequency. That equal 1 over 2 pi times R times C. Okay? Pi 3.142. Okay, any question in this part here? Okay, now, one pole, okay? The zone off rate will be minus 20 dB per decade. 2 pole, 2R to C, zone off rate will be minus 40 dB per decade, or 0.01. 3 pole, 3R, 3C, zone off rate 60 dB per decade, or 0.001. Okay, so basically, good filter will be have to be more than three poles. You understand in your cell phone, you must get the filter. And you can see how come one cell phone cheaper the other one. You make the very important thing in your cell phone, that means the filter. And also another device, A to D converter or D to A converter, analog converting to the binary or binary converting to the analog. That completely quite different pricing. Okay? For the filter, you can build easy with I and C. Okay? However, in your cell phone, they will be more complicated, cost more money. Okay? Now, you can see this circuitry here. Very simple. You get R and you get C. Only R and the C. Okay? So when you get a 10 volt peak to peak coming in, okay? So you see the output of the filter. This range right here, mid range. That means V in 10 volt, V out 10 volt, no loss. Okay, now at the cutoff frequency, okay, if you get the one pole low pass filter, they down minus 20 dB. When the frequency increment 10 times of the cutoff, I given you example, 1K here, then that will be 10 kilohertz. 2 pole, they will be down 40 dB per decade, and 3 pole down 60 dB per decade. So which filter you think will be the best in this example?
Hey, Mr. Pham, I know you said the 60, but my question is, you got FC at the bottom, then you got 10 FC, then 10 FC. Shouldn't the second one be like 20, shouldn't it be 10, 20, 30 or something like that?
What do you mean 10.30? Okay, now,
Why do you have
go ahead.
why do you have 10 FC, 10 FC?
Okay, now, I suppose to draw only one, only this one. That's 10 FC.
Right.
I draw another one for this guy. Same thing, 10 FC. You see that?
Yeah, but isn't the frequency, as you go to the right, isn't the frequency getting larger?
Yeah, they will be higher.
In other words, you got a frequency at minus 60 dB, and you got a frequency at minus 40 dB, and you have a frequency at minus 20 dB. Shouldn't the frequency at minus 20 dB be a lot bigger than the one at 40 and 60?
Now, that is 1 kilohertz,
Right, correct,
and that will be 10 kilohertz.
right.
That will be 10 kilohertz. That will be 10 kilohertz. What I'm saying is, I suppose to draw one for 20 dB. I draw another one for 40 dB. I draw another one for 60 dB. However, I want to compare between minus 20 dB, minus 40 dB, minus 60 dB. Just telling you guys which one is the best. You want it,
Minus 60.
minus 60. Why minus 60?
Roll off rate's faster.
The thing is, they want to stop the signal you don't want after the cutoff. That's what we're talking about, stop band. We want to stop as much as we can. Okay, otherwise you can get more noise. Okay, so minus 60 dB will be the best for this example. On your cell phone, maybe they will be minus, they will be minus a very big number. They want to cut it off right away. Okay, the good cell phone, when you're talking to your friend, you recognize your friend's voice right away. However, some different phone, your friend voice, elder, you cannot recognize. Okay, that is the thing is not good filter. That is the thing is different price for your cell phone. So now you understand. You can get a minus 20 dB or 40 dB or 60 dB. Okay. So
So, Mr. Pham, basically, you're just showing that the higher number dB is closer to the cutoff frequency.
exactly.
And since it's closer, then whatever's at the top of the, whatever's where the zero is at, it will go down faster.
Exactly.
Okay.
Understand. This is pass band allow signal to pass
Right,
from the cutoff go this way.
right.
Because stop band. You want stop as much as you can. You don't want still get the signal here. Okay? You want this one, go down right away. Okay?
Mhm. Okay.
And if you want to calculate the cutoff frequency again, 1 over 2 pi RC. If you want to calculate the output at any frequency, you have to do in this formula. But we don't need to do it. Okay? You guys don't have to do it. You're going to learning how to design the filter. Okay? More detail, like a college or university, then you can worry about this thing. Otherwise, when you're looking in the circuitry, you're telling me this is a low pass filter. And you're telling me the cutoff frequency is what? Okay? Now, I want you to do calculate the, oh no, that is, they go to another one, IL. We just get through the IC. Now they just give a picture for IL. That means inductor and resistor. You can see the difference. Okay. For the capacitor, low part, C here, R here. However, if they're using IL, then L will be here. Okay. Different position. And the formula to calculate the cutoff frequency equal R divided 2 pi L. Okay, they working identical. Output is at any frequency. You have to using this formula. But we not deal much with the IM. Most of the low part will be IC.
Why do they like to use the capacitor over the inductor?
That's normal.
No. I'm saying, is there something that the inductor does or the capacitor does to make one or other the better?
For sure, I believe capacitor better. So that's why I saw most of the filter will be IC. Very, very few with the IM.
Okay.
But I still bring it up for you guys. Okay. Now, by part capacitor. If you're looking in this circuitry here, you get R1, R2, and the capacitor here. But they not low part. This capacitor, they go by part.
Bypass R2.
Yeah. What they want to bypass.
R2.
That will be telling you if you get a sideway here coming up here. Okay? If the capacitor is bypassed, they short it to the ground. So this signal cannot go through R2. So basically, in this case, capacitor bypass R2. Now, capacitors are connected in parallel with a resistance for the purpose of bypassing or sending AC signal around the resistance above a specified frequency. The above circuit shows a bypass capacitor C1 connect across R2 to bypass R2 effectively. I see that means capacitor reactance value must be 1/10 of the value of R2. Okay, the result is practically zero AC voltage across R2 for the frequency that produce AC value 1 kilo ohm or less. The circuit is definitely a low pass filter. So make sure they can be bypass, guarantee bypass 100%. Then they're telling you the value, okay, actually must be 1/10 of the value of R2. Okay, so for this circuitry, actually you think supposed to be
Well, X of C is 1K, right?
1K. right?
Because you said it's got to be 1/10 of R2.
Right.
And
And
1/10
then,
of R is 1K.
yeah.
One kilo.
So actually doing calculation, they must be 1 kilo ohm. Okay? Guarantee they can bypass any on the signal go here. Okay, so basically that one, I'm not giving you most of the calculation, but in general, okay, we're talking about any calculation later. Right now, I want you to looking into the circuitry to recognize is it a low pass filter or the high pass filter and how it works. Okay, next thing, I say high pass filter. Pass any frequency higher than cutoff frequency. Okay, cutoff frequency formula is the same as a low pass filter. That means 1 over 2 pi RC. So for this circuitry, you can see that circuitry different from the low pass. Low pass capacitor will be here. R will be here. Now they just change the position C and R. They working like the high pass filter. Okay. Now this is the cutoff frequency. Any signal higher than cutoff, they are allowed to pass. Any signal less than cutoff, they will be blocked. So that will be called a stop band, or stop band here. Okay, that will be called a pass band or bandwidth. Okay, so you see this is just the opposite to the low pass filter. Low pass filter pass any signal lower than cutoff frequency. High pass filter will be allowed only the signal higher than the cutoff to pass. Okay, and also they given to you the circuitry IL, high pass. Same thing like this one. They just change the position L and R. They working the same thing. Now, next one. Band pass filter. This is just a general. We'll get a one lecture detail on the band pass filter. The thing that we'll be using a lot. And also band pass filter related to the resonant circuitry. So that's why I will be talking about resonance before I going back with the band pass filter. Now, band pass filter, pass frequency higher than F1 and less than F high. So basically, for this band pass filter to get a two cutoff, one will be low frequency, one will be high frequency. And also that is the cutoff minus 3 dB right here. You get a 1 point here, you get another point here. That's the cutoff low frequency, high frequency. So any signal higher than F low, less than F high, they are allowed to pass. That you're looking into here, they say pass band or bandwidth. Okay. frequency response, let me know. Output of the frequency. Okay. So from F low to F high, that's what they call a pass band. Okay. After F low, higher than F high, that will be a stop band. That is a band pass filter. And most of the things using in the equipment, they're using band pass filter. Any question on this picture here? Let's see. Bandwidth equal F high minus F low. That means higher cutoff minus lower cutoff. You get the bandwidth. You can see right here. The quality scale of the filter equal F center divided to the bandwidth. This is the F center right here. Okay. And the bandwidth you already know here. Okay. Quality scale control the runoff rate and the bandwidth of the filter. That will be telling you get better Q, then the filter will be better. That's a minimum thing. When you see that output signal, you're able to tell, okay, what is the bandwidth of pass band, which one is the stop band, which one, okay, will be the cutoff. You get lower cutoff and the high cutoff. And if you want to calculate the bandwidth, you get the F at a high frequency cutoff minus F at a low frequency. Okay? Anything up to this point.
F1 and F2, F1 and F2, where is it?
Now that's a cutoff frequency identified by minus 2 dB. You see, you get 2 points at a minus 3 dB. And you understand the minus 3 dB. That is the cutoff at the cutoff frequency. So that's why you can get 2 points. Basically, if they want to make a band pass, they adding high pass filter and the low pass filter. That given you band pass filter. But I said for now, we not flow detail. I get a separate lecture for the band pass filter. But that is just a very, very general. And the last one, band stop or not filter. They just basically opposite to the band pass filter. They also get the two cutoff, F low, F high. Okay? And they allow any signal higher than F high or less than F low to pass. Okay? Any signal between F high and F low, they want to stop it. That's what they call a stop band. They just opposite into the band pass filter. Okay?
Okay.
Now we go see some few things here. You can see that is the output of the filter. Okay, how they cascading filter section, narrow the bandwidth, and improve selectivity. Okay, so basically, if I'm looking in this the one, you want this one, 4 section, 4 pole. Okay, this is the worst one. 1 pole, 2 pole. The reason we like 4 pole section here, okay, that means they are narrow band, so you don't have a much noise. For this one, okay, the cutoff will be low, so that's why a lot of noise. That is, they just bring it up for you to see difference between 4 pole or 3 pole or 2 pole low pass filter. And now another one that is given to you. This is a filter for X designer. Okay, capacity, elliptical, butterworth, best cell. Okay, same low pass filter. And now which one will be good or which one is not? And you understand the ripple here. What is it? What ripple?
Noise.
What is ripple? What is it?
The passband.
Now,
Unwanted signal.
You mean AC, you mean AC riding on DC?
no. Ripple. What is it? That's just a noise.
I thought somebody said that.
You have to know it. Noise means what?
Static,
Un
unwanted signal.
unwanted signal. Okay. Normally you can see ripple will be on the top of the DC, right? 10 volt or 5 volt. On the top, they get the ripple. That means they get the noise. When you design circuitry, like I did it in the company for the government, they will be asking you how many percent of ripple to be accepted. Maybe 0.001%. So when we done the unit, we must be testing to guarantee the ripple have to be less than what? That number. Okay? So ripple for now, try understand they just a noise, nothing else. Unwanted signal. Okay? So for this one, you get a capacity, elliptical, butterworth, and best cell you see which one will be the best for engineer. They design low pass filter. Which one is good
The Bessel,
and how they
The
will be good.
so the Bessel,
Which one you see the best one?
the Bessel.
Chippy chip.
Okay, now you see Jeopardy right here. They very good for the cutoff, right?
Too
They,
much,
they close to the idea, very close. However, they get a problem.
too much noise.
Too much
Noise.
noisy. Okay? The cutoff very good, better than the other. However, they get too much noisy. How about elliptical?
Same.
Cutoff is not really good, right? After this guy, but they will be not much noisy, right? You say that? No noise on elliptical. How about butterwood? That guy.
That's not good for only pancakes.
Yeah. That is no noise. But the cutoff is
Too-
not really good.
Yeah.
How about the best cell?
That's the best one.
The best one.
It's the bad one.
The thing is they have a no ripple. And also the cutoff, they still better than butterwood.
That means the roll-off rate is better, right?
Right. Drawn up better than this one, but not better than this one and this one. However, Cavity electrical get too much noisy. Okay. I try to understand for this picture. Okay. The thing is, they will be asking you when you get interviewed. Most of the big company in San Diego will be a defense company. Okay. They just want to know you get a basic understanding or not. Okay. So they can ask you for those or not the low pass filter, which one you prefer or you like. Why? Okay. Yet no more. Or what? Yeah, no more. Okay. Now, I get another one. I just given a few things on that handout. Make sure you download that, okay, and try to read through it. Okay, now I go with only low pass and high pass, not band pass. In your left row. Okay. A filter is a frequency. Okay, selected circuit that permit signal of a certain frequency to pass, while it rejects signal at other frequency. Now, we already know. You just see on the left wall, RC low pass, RL low pass. They already given you. Okay? In order for recognize which one, low pass filter, RC or RL. A low pass filter, as its name implies, pass low frequencies but reject high frequency. Okay, so make sure if you want to ask question or confused, stop me. Okay, I try to explain to you. Now, this is the same thing we already saw it. Okay, the driving line between passing of low frequency and the reject high frequency is the cutoff frequency or minus 3 dB point. You can see that this is the mid-range. Okay, right here, minus 3 dB. That means cutoff frequency, FC. And that is the frequency domain. Okay, that is the output voltage. If you want to say in the frequency domain, you have to using spectrum analyzer. Oscilloscope is the time domain. Okay, so that's why for the frequency domain, even you get a sine wave coming in, but you cannot get any sine wave display on the spectrum analyzer. The thing is they vary with the frequency, not vary with the time. Okay, oscilloscope, a time domain. In the high pass filter, signal higher than the cutoff frequency, pass, okay, essentially unmodified. Signal lower than cutoff frequency are greatly attenuated or reduced. Okay, we already know that. Now, low pass filter has a cutoff frequency of 10 kilohertz, a band of frequency ranging from 20K to 100K. A pass essentially unmodified. B greatly attenuated. LB.
Okay, okay.
A or B, 50-50.
B.
B. Low pass filter, cut off 10 kilohertz. That means any signal from 0 up to 10 kilohertz, that will be a pass band. They are allowed to pass. Any frequency higher than 10K, that is a stop band. They want to stop it. So, signal ranging 20K to 100K, they basically a stop band or greatly attenuated. Attenuated, that means going down. That is the answer. Now, the cutoff frequency is the point where the output voltage dropped to 70.7% or minus 3 dB down from the input voltage. That's what we already telling you. Okay. Frequency response data, that means output, may be expressed in terms of output voltage, but it is usually expressed in decibel. Okay. Decibel are units that express or measure the gain or loss attenuation in a circuit. The decibel can be based on the ratio of the output voltage to the input voltage. We already learned dB equal 20 log of VL divided to VE. Note, in the type of filter studied in this volume, the output voltage is always less than the input voltage. Okay, so for this low pass filter, high pass filter, passive, maximum output will be equal to the input. Output cannot higher than the input. The thing that they have a no gain. Gain equal 1. Input, output, the same. Okay? So that's why when you're working on the low pass filter circuit board, you can see that thing. Make sure they're telling you, okay, output always less than, okay, input voltage, or equal or less than, okay. So that is the last one I want to talk to you today. That is the same thing here. We already see that. Rate of attenuation or loss by on the cutoff FC is highly predictable. Attenuation is 6 dB per octave or 20 dB per decade, and attenuation rate of 6 dB per octave is the same as the rate of 20 dB per decade. They working same thing. Okay, so we'll be continuing on Wednesday. Make sure you download the new handout, including this one. Okay, and another one resonant. Try to read it over before we can get a lecture. Okay, only thing you try to understand. Only understand you can memorize it for long. Okay, I don't care much about test or whatever. I only think make sure when we go through the lecture, you're able to understand. Okay, any question or anything?
Yep, I have a question, teacher.
Yeah, go ahead.
Is the attenuation always a negative value?
What do I mean?
It's a negative. The attenuation,
Negative what?
the negative value, the attenuation is always negative.
For sure. Attenuation means you lost. You see that? You lost.
Yeah, yeah.
You get 10 volt coming in. You get 7 volt coming out. You lost 3 volt. However, all the time have to be negative. Why? The thing is 0 dB. That means right here, input output the same. That means the gain equal 1. However, when you go to the cutoff right here, they drop to 70.7%, equivalent to minus 3 dB. That is the ohm have to be
Okay.
minor. The thing is, we
Okay.
lost. Okay?
Okay.
Okay. If no question, then good night, everyone.
Good night, teacher. Good night,
Good
everyone.
night.
Mhm.